Welcome to clickmyproject.com. Let's discuss about the product. Our product is exploiting the incomplete diffusion feature, a specialized analytical side channel attack against the AES and its application to microcontroller implementations. Algebraic side channel attack ASCA is a typical technique that relies on a general solver to solve the equations of a chipper and cipher, and it is side channel leaks. It falls under analytical side channel attack and can recover the entire key at once. Many algebraic side channel attacks are proposed against the AES, and they utilize the Grosvenor basis based, SAT based or optimizer based solvers. The advantage of general solver approach is its generic feature, which can be easily applied to different cryptographic algorithms. The disadvantage is that it is difficult to take into account the specialized properties of the targeted cryptographic algorithms. The results vary depending on what type of solver is used, and the time complexity is quite high when considering the error-tolerant attack scenarios. Thus, we are motivating to find a new approach that would lessen the influence of the general solver and reduce the time complexity of ASCA. This paper proposes a new analytical side channel attack on AES by exploiting the incomplete diffusion feature in one AES round. We named our technique Incomplete Diffusion Analytic Side Channel Analysis, that is IDASCE, different from previous ASCAs. IDASCA adopts a specialized approach to recover the secret key of AES instead of the general solver. Extensive attacks are performed against the software implementation of AES on an 8-bit microcontroller. Experimental results show that IDASCA can exploit the side channel leaks in all AES rounds using a single power trace. It has less time complexity and more robustness than previous ASCAs, especially when considering the error tolerance attack scenarios, and it can calculate the reduced key search space of AES for the given amount of side channel leaks. IDASCA can also interpret the mechanism behind previous ASCAs on AES from a quantitative perspective, such as why ASCA can work under unknown plain text ciphertext scenarios and what are the extreme cases in ASCAs. The communication process are still used in many applications today. The first and historically most important application for communication satellites was in incontinently long distance telephony. In previous, the design of AES are held in various part implementations such as round key mechanism. In this, we proposing the algorithm to improve the security of system and reduce the power consumption by encryption and error correction method, especially for side channel. So this is the system flow of our design. Here initially we are applying bits as input to the system. So that means we are producing the key to encrypt the bits. So after producing the key to encryption, that is the encryption key, that processes a round key mechanism. So that round key mechanism generates the key, that is a generated round key. So that validates the checking key and then it's processing to the encryption, that is AES. Here AES is combined with LDPC, that is low density parity check. So finally, by using that encrypted text by using the key which is rounded, finally it provides encrypted result. So finally, after getting encryption result, the same procedure reverses for decryption mechanism. Let's see the running procedure of our AES process. Here we have processed the design system with combination of MATLAB and Xilinx. Here initially the code in MATLAB processes the key, and then the bits which I have to encrypt is converted from text to bit, and the bits are passed to Xilinx. So here main function.m, this is the main file which we have to run. So after running that main file, we will get a small menu bar. So we have executed the main function.m file. This is a MATLAB file. So here what we have done is we have read that input text file which we have to encrypt. That encrypt text is converted from text to bits, and the converted bits are going to pass to Xilinx. So I am selecting the option which what I am going to do. I have selected encryption. So for encryption what I am doing is just I am passing a key, which is the key I am using for encryption. So at this time that Xilinx bar is opening. So the process from text to bits are converted, and the converted bits are passed to Xilinx ISE simulator. So here is our process. Here what I am going to do is I am just running this, simulating this code. So it will take some time to complete the simulation. Here simulate behavior model, we have to select the main module here, and we have to click simulate behavior model, and then iSim will open. Here what we have to do is we have to apply the parameters, force constant. So I am setting the values and making enable as 1. So I am running the procedure, and finally the bits are encrypted. So now I am going to see the encrypted result in MATLAB. Here while I am clicking entering any button, so the cipher text will open here. So for the decryption also we have to do the same procedure. Here for the performance of encryption we can click this menu bar. So after that clicking the menu button, we will get the performance results. So this is the cipher text. So for the decryption also we have to use this same key to decrypt this text. So this is the time delay or comparison between existing and proposed. And this is the statistics on number of correct key bytes. So I am doing the same thing for decryption. I am choosing decryption, entering the key. Thank you.